Hello, students, and welcome to today's video help, where we are going to essentially be going over the Le Châtelier principle worksheet number 3, because it was asked for us to go ahead and work on this worksheet here. So, just a reminder that Le Châtelier's principle is the principle that states that when we add a stress to the system, the equilibrium is going to push towards the opposite way to kind of counteract that stress. Okay. So for number one, what we're going to look at is we have a reaction that is H2 gas plus I2 gas, and that makes 2HI gas, hydrogen iodine. And it looks like it ends up having a positive enthalpy change. Okay. And so right away we can tell that since it has a positive enthalpy change, we can see that the reaction going from the left to the right is endothermic because it has absorbed energy. And so our thought process is going to involve that here in a little bit. Okay. Question A says that if we add more I2 to the vessel, the forward reaction will blank while the reverse reaction blinks. Okay. So if we add more reactants to the reactant side, that means that the forward reaction is going to increase and the reverse reaction will decrease at that moment. Okay. B, if HI gas is removed from the vessel, the forward reaction will, well, if we're removing something, then the other side is going to increase. So in this case, the forward reaction is going to increase, while the reverse reaction is going to decrease. Okay. For C, if catalyst is added to the vessel, the forward rate will stay essentially the rate of change is going to end up staying the same. Okay. So the rate is going to stay the same, the reverse rate will stay the same. The catalyst lowers the activation energy for both the forward and the reverse reactions and speeds them up equally. Okay. So in the case of C, I misspoke because our amount is going to end up staying the same. A catalyst will increase the rate of both of them. Okay. So both will increase, and then eventually what will happen is that the increases are going to be exactly equal. Okay. For number 2, considering the following equilibrium system in a closed vessel, N2O4 is a colorless gas, while NO2 is a red/brown gas. Okay. Predict what will happen to the color of the gas mixture in the vessel, lighten/darken, if more N2O4 is added. Oh man, I should change that here. Okay, so if you add more N2O4 to the vessel, what's going to happen is that, initially it's going to be clear, okay, because N2O4 is clear, but as you add more, as it goes along, what's going to happen is that it's going to darken because you are pushing that equilibrium to the right, okay, because you've added more to it. So A is going to be darkened. The next is the volume of the vessel increases. So you want to imagine that you have a vessel, that it's a closed vessel, and then you increase the volume. When you increase the volume, the pressure is naturally going to decrease. Therefore, if the pressure decreases, it's going to affect the side that has more number of moles. It's trying to keep that same amount of pressure in equilibrium. So if you decrease the pressure, what will happen is that you're going to push it towards the right. The logic behind this is that now that there's more pressure, now that there's less pressure, less NO2 collisions are going to be happening, and therefore the reverse reaction gets reduced in this case. Okay. The last has to do with the system being cooled down. Okay. So the forward reaction here ends up absorbing 57.2 kilojoules per mole. Since it absorbs 52.7 kilojoules per mole, that means that it's endothermic. Okay. Which means that we are going to end up slowing down the forward reaction. So we're going to go ahead and push it to the left. Okay. Next is question 3. And question 3 was nice enough to go ahead and give us a graph. And for question 3, it's saying that a student is holding a test tube containing a solution, and it has zinc iodate in it, and we get zinc ions and iodate ions. Okay. And it wants us to identify the stress that's applied at T1. Okay. And what we can do is we can go ahead and look at our graph right here, and we can see that we have a huge increase here. The only way we can get a huge increase like that is if we add zinc to our solution. So therefore, A is going to be that we added a large amount of zinc ions. Okay. And then it wants us to go ahead and sketch the change in IO3 when that happens. Okay. So we added a whole bunch of zinc ions, and therefore if we added zinc ions, what are we going to do to this IO3? Well, when we add to this side, what'll happen is that we will go ahead and push it to the left. Okay. And since we didn't add any IO3 ions, what's going to happen is that when we push it to the left, we're going to use more of these ions. And when we use more of those ions, what'll happen is that we're going to have our initial state here. So we have our IO3. We have our initial state. But then because we added more, it's going to decrease slowly until a new equilibrium change has been met. Okay? And that's because we added more reactants to that particular side, that one side. We added more reactants to the left side, the right side. And it'll push it towards the left side. Okay? C, assuming that all the ions are colorless in solution, what evidence would there be seem to indicate that the equilibrium is shifting? Okay, so in addition, we would be able to see, we would have to look at these states. Okay, so it says that the zinc ion is aqueous, the iodate ion is aqueous, but the zinc iodate ends up being a solid. Okay, therefore, if we shift to the left, we should expect to see more of the zinc iodate becoming a solid. Okay. Next, the student noticed that the test tube became noticeably cooler during this shift in equilibrium. Okay, so since we're shifting this to the left, that indicates that the reaction going to the left absorbs some energy. Okay, so therefore we're going to think, oh, okay, zinc plus iodate ion is an endothermic one. Reverse reaction is endothermic. Okay. The student noticed that the test tube became cooler. Is the reaction written above the graph exothermic or endothermic? Okay. So typically, when we determine our reaction, we go from left to right. Okay. And if we go from right to left and it's endothermic, then left to right should be exothermic. Okay. And that's going to go ahead and close out for this little review section on section 3 on Le Chatelier's principle. Again, today, if you do end up having more questions, please go ahead and ask them today so that we can go ahead and make sure that your knowledge is set and ready. All right. Until next time, remember, stay lazy.